Hello, I thought I would say a few things about numerical methods in general and give an example of why one needs to be careful with some of them. We will not analyze numerical methods. We're assuming that the technology that we're using has paid attention to being somewhat accurate. But a numerical method is a discretization. We assume that we take time steps and calculate based on those time steps. And the accuracy of the method can be analyzed, but we won't do that. So let's look at Euler's method. The idea is that you know what the derivative is because you're given what the derivative is a function of the variable x. And so if you have some starting value and you have some time step, then you know that the derivative at the starting time depends on the starting value, so you can calculate what it is. Then the value at the next time, after having taken the time step, is approximately the starting value plus the time step times the derivative. And so that gives you the next value. Now I wrote equal, that's equal in the method, but it's of course an approximation to the solution to the equation. Then we do that again, and so now we are at time 1. We're calculating the derivative based on our equation. We find out what it is. In this case it's -1, and then the value at the next time is the value at the start plus the derivative times the time step. And so in this case we get x1 was 1 and -1 is 0, which happens to be exactly the value we had before. And so the value for x2 is 0, the value for x3 will be 1, the value for x4 will be 0, and back and forth it goes the whole way. Now this equation is actually one we can solve, so we can compare the actual solution to the numerical solution. Of course we've chosen a very bad time step in this case because with a different time step the behavior might be better. But the point is that you can't assume that the numerical method is giving you a solution unless you've analyzed that it does that. So here's the actual solution to the equation with x of 0 equal to 0. Particular solution is a half. General solution to the homogeneous equation is e to the negative 2t. And then we see that's the solution. So x at 1 is in fact 1/2 minus e to the negative 2. E to the negative 2 over 2, that's about 0.4323. So it's not 0 or 1. The solution, the numerical solution, is not stuck close to the actual solution, and certainly not further on, right? The first x1 was 1, so that was an overshoot, and x2 was 0, and again, x2 is still going to be positive, and so on.